Hello, Honors Chem students. Mr. Keister here with you again today. This is the video for Thursday, October 1st, 2020, which is our scheduled 30th day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's take a look at our do nows and see what our schedule is for today. So today you are to pick up our new assignment, page 45, on thermal energy, phase energy, and a heating or cooling curve. The big thing you're picking up today is Fall Semester Review 1. I will talk to you about that here in just a couple of minutes. From yesterday, we had our new notes packet for Unit 2.2 on energy and our first assignment. Wanted to let you know that your exam 2.1 is graded in the grade book. The average for all 4 classes combined was in the mid to upper 80s, which is good. I should have them back to you tomorrow or probably Monday at the latest. Got a few students yet who haven't taken it. So your homework for today was to complete the Unit 2 energy reading quiz in Canvas. That was due at 7:30 this morning, so hopefully you all remembered to do that because that is now shut off. Okay. Today we'll be starting the second half of Unit 2 involving energy. We'll talk about the different energy accounts and how a heating or cooling curve is constructed and interpreted. Okay, you'll have an assignment over this that is due tomorrow. Now, about that review. You have extra work for this coming week outside of class. Unit 1 and Unit 2.1, so that's all of Unit 1 and half of Unit 2. Review assignment is the first review for the fall semester final exam. It is actually the first of 3. All right. You're to work on this on your own time. It is due this coming Tuesday at the beginning of class. This coming Tuesday at the beginning of class. So this is outside additional work in addition to our normal routine. There are no answer keys posted for these reviews. No answer key posted. So I would suggest that you communicate with friends and classmates and compare notes, compare your work before you turn it in. All right, that is good advice. So maybe you can catch either mistakes of your friends or mistakes of your own by doing that. All right, so no answer key posted on these semester reviews. And again, this is the first of 3, and it is due this coming Tuesday at 7:30 a.m. All right. I'm sorry, not at 7:30 a.m. It would be if you were period 1. It's due at the beginning of your class, excuse me. All right, so let's take a look at our notes for today on energy. All right, there we go. So, Unit 2.2. So, in the 18th and 19th centuries, scientists wrestled with identifying and describing the nature of the stuff that produced change. One concept that became popular for a while was that of the term caloric, which we now call heat. Of course, caloric is the root word from where the word calorie came from, which is, of course, the metric unit of energy. So caloric was originally conceived of as a quantity that would flow from a hotter object to a cooler one that would then warm up as a result. It answered the need for a way, the cause of warming, to get from one place to another. Not only did caloric serve as a cause for warming, it was also considered to be the cause for changes of phase. In other words, going from solid to liquid, melting, liquid to gas, boiling, etc. Caloric enabled particles of a substance to move farther apart until the attraction of the particles became too weak to hold them together. We talked about that before. You know, solids have very strong attractive forces between them. As such, they have a definite shape and definite volume, and they can't flow. But as they get farther apart, those attractive forces weaken. The particles spread apart a little bit. Now they become a liquid. All right. Liquids can hold their volume, but not their shape because the attractive forces have weakened. And once you then get them far enough apart and they go into the gas phase, there are no attractive forces between them at all. All right. And so they have an indefinite shape and an indefinite volume, and they have gone into the gas phase. All right. Although Antoine Lavoisier did not think that caloric necessarily was an actual substance in its storage and transfer, it was like a substance somehow. So when scientists recognized that the stuff involved when forces were applied to objects to lift them or change their speed, as such as you probably discussed in physics or will, was the same stuff that was involved when the temperature of objects changed, they worked to develop a single energy concept. All right. So when the energy concept was developed, it was important to distinguish it from caloric. All right. And snuffing out the caloric concept, the clear picture of energy storage and transfer that it fostered was unnecessarily lost too. So even though we recognize that energy is not a physical substance, we choose to use the term substance, as a metaphor in order to describe it. Okay. We will use three principles to guide us in the development of the energy concept. Number one, energy can be viewed as a substance-like quantity that can be stored in a physical system. Number two, energy can flow or be transferred from one system to another, and when it does, it causes change to that system. Number three, energy maintains its identity after being transferred. All right. So if you're unsure what we mean by the use of a substance metaphor, let's look at another example. Consider how we describe information. We say that it can be stored in a book, a computer hard drive, a CD-ROM, a flash drive, etc. Information can be transferred from place to place via cables or by wireless transmission technique. In fact, you do this when you access a lesson via the internet. Transfer it to your computer, and then perhaps print it off. There's nothing substantial about the information itself. You can't touch it. You can't measure it on a balance. All right. The third point is important to consider because many texts talk about energy transformations as if somehow the energy is changing rather than the system that gains or loses the energy. To consider the information metaphor again, even though we move information from one place to another or store it in a different way, nothing about the information itself has changed, and thus nothing about the energy has changed either. The system changes as a result of a loss or gain of energy, but the energy itself doesn't change a bit. Okay. So, energy storage and transfer. So at this point, let's consider another metaphor to describe energy storage and transfer. Let's look at money. All right. We can store money in accounts at a bank or a credit union. We can have a checking account, a savings account, a certificate of deposit, a money market account, et cetera, et cetera. All of these accounts store money. There's nothing different about the money in a checking or savings account. The money can be transferred back and forth in the bank without changing the nature of the money or the total quantity of money that resides in the collection of accounts that are attached to your name. So let's just call this the system for convenience. The same exact thing is true of energy. It's stored in objects and in the arrangement of those objects in a physical system. We use different accounts to help us keep track of energy as its transfer causes change in the objects or in their arrangement. As with money, nothing about the energy itself has changed. All right, so let's look at the three energy accounts. All right, three energy accounts. First of all, is thermal energy. All right. Thermal energy is the energy stored by moving particles. All right. Quantity of thermal energy stored by a collection of particles is related to both their mass and velocity. This is kinetic energy. Okay. You instinctively recognize this as you would rather catch a barehanded baseball thrown by your instructor, yours truly, than one thrown by a major league pitcher. I can vouch for that. Similarly, you wouldn't be hurt if you were pelted by ping pong balls, but it would suffer if you were showered with golf balls going at the same speed. All right. Thermal energy, or ETH, is represented by temperature. So a change in thermal energy results in a change in temperature. All right. Change in temp, change in thermal energy. Okay. Second is phase energy, or EPH. Some texts call it EI, as in interaction energy. We're going to call it EPH, all right? Phase energy is the energy stored in the system due to the arrangement of particles, all right? The arrangement of particles that exerts attractions on one another. Attractions result in a decrease in the energy of the system of the particles because if they're closer together, they can't move as well, right? As particles become more tightly held, their phase energy is then lowered. Solids possess the lowest phase energy, liquids possess somewhat more, and gases a way more amount, all right? Phase energy is represented by a phase or state of matter. Either solid, liquid, or gas, okay? Again, some texts call phase energy interaction energy or EI. We are going to stick with phase energy or EPH. So gases have the greatest amount of phase energy since they have completely broken free from one another. So EPH is the energy account involved when a phase change occurs. So let's look at a heating curve, all right? Let's look at one for water. Heating curve for water at standard temperature, or I should say at standard pressure. Because it's at standard pressure that water phase changes occur at 0 degrees Celsius and 100 degrees Celsius, okay? Ice melts or water freezes at 0 Celsius, 32 Fahrenheit. And water boils at 100 degrees or steam condenses at 100 degrees at Celsius, that is, 212 Fahrenheit at standard pressure, right, at standard pressure. So this is temperature on the Celsius scale, and this is time. So of course, we go this way, more time has elapsed. As we go this way, of course, the temperature increases. So this would be what we call a standard heating curve for any substance, but we're going to talk about water. So what we have here then is the solid phase, all right, solid phase. And as you take ice, so this is water in the solid phase, which would be ice. As you take ice and apply energy to it, it warms up, all right? But it's going to stay ice until it gets to this temperature right here, which is 0 degrees. 0 degrees Celsius, okay? If you continue to add energy to that ice, of course, at 0 degrees, it's going to melt. But what I want you to see is this. While it's melting, so this is solid, the liquid, all right, which we call melting. Notice that the temperature is not changing, all right? This is because as it's going from some temperature below 0 up to 0, its temperature is increasing. A temperature change explains the change in thermal energy. So thermal energy is changing here. However, when we go from solid to the liquid phase, the melting phase, we are changing its phase energy. Phase energy is not represented by a change in temperature. It's represented by a change in phase or a change in state. And so as you can see, while the ice is melting, the temperature remains at 0 Celsius. The energy that's being applied to the ice to melt it is now phase energy. It's a different account, all right? It's a different account. Once we get to this point where all of the ice is melted and continue to add energy, now that liquid water warms up. So now we're in the liquid phase, and as we see again, we're getting a temperature change. Now thermal energy, the thermal energy account is in again, all right? So now a change in thermal energy is occurring. And it will continue to raise its temperature until we get to the next phase change for water, which is at 100 degrees Celsius, all right? 100 degrees Celsius, which is where it boils or vaporizes. All right. And so now we're going from liquid to gas, which we call boiling or vaporizing. Either one. The liquid's turning to a vapor, hence the term vaporization. And now, again, the temperature remains constant while that's occurring. So we're now, our account is switched again to phase energy. And then finally, if we vaporize all the water and continue to add energy to it, that the temperature of that steam or water vapor will continue to increase. We're now in the gas phase, and now we're showing a change in thermal energy yet again. So this is energy being added. This is a heating curve, all right? It's a heating curve. And as you can see, there are 5 sections of this graph. 5 sections to complete the curve. If all 3 states of matter and both phase changes occur. What do I mean by 5 sections? Well, they're right here. So the solid phase is 1, solid to liquid, the melting phase is 2, the liquid phase is 3, the boiling or vaporizing phase change is 4, and the gas phase is 5. Okay, so 5. So that is called a heating curve. What do you think a cooling curve looks like? Just the opposite. All right, just the opposite. Only instead of energy being added, now energy is being removed. So the substance cools down and it undergoes phase changes from that cooling. Okay. In other words, now a gas would go from a gas to a liquid, which is the opposite of vaporizing. We call that condensing or condensation. And then, of course, going from liquid to solid, which is the opposite of melting, which we normally call freezing. Official term is solidification. So cooling curve looks the same, just in the reverse, right? Instead of looking like steps going up, it looks like steps going down. The third energy account is chemical energy, all right? It's the energy due to attractions of atoms within molecules. So this is bonding, all right? These attractions are described as chemical bonds because they're directed between specific atoms in the molecule. Chemical energy is represented by identity. All right. There's no change in chemical energy here because the substance's identity remains the same. This is water. This particular one is water, regardless of what state of matter it's in. It's still water. All right. So this is a physical change. Phase changes are physical changes. Increases in temperature are physical changes, not chemical. If a chemical change occurs, then we have a change in chemical energy. Okay. So there are also 3 ways that energy is transferred between a system and its surroundings. While most texts refer to them as nouns, work, heat, or radiation, we prefer to describe the ways as gerunds to emphasize that they're processes rather than real things apart from energy. So we call them working, heating, and radiating. All right, working W, heating Q, and radiating R. It's very important to recognize that such energy transfers affect both the system and the surrounding. If the system's losing energy, the surrounding's gaining it. If the surroundings are gaining energy, then of course the system is losing it, and vice versa. All right. Energy doesn't mysteriously appear or get lost. It's always there. It's just gone somewhere else. All right. It's gone somewhere else. So the first one is working, which is usually referred to as work by the physics people. All right. Oh, it's not something different from energy. Okay. Working is just one type of energy transfer. All right. It's the way in which energy is transferred between macroscopic, large enough to be seen, objects that exert forces on one another. It's okay to calculate how much work one object does on another, so long as you do not think that work is something an object stores. All right. Then we have heating, or Q. That's referred to as heat by the chemists. All right. Heating is the way in which energy is transferred by the collision of countless particles. All right. Energy is always transferred from the warmer object to the cooler one, because the warmer one's particles are moving faster. All right. They're moving faster. So if all the particles have the same mass, then the hotter ones are moving faster than the colder ones, which you just said. So it's okay to say that you heat an object, just not that the object stores heat. All right, it stores energy. Okay. Radiating is the third one. This is R. This is the process in which energy is transferred by the absorption or emission of photons, which are particles of light. We'll get into that in an upcoming unit, not too far away from now. So a light bulb filament can be heated to the point that it glows. This is the emission of photons that carry energy away from the filament, and thus you see them. You can be warmed by light from the sun as the photons transfer energy to you. This particular type of photon, it's called a photon of infrared energy. All right, it's a particular type. So the relationship between energy storage and transfer is given by the first law of thermodynamics, all right, which is the change in energy of a system is equal to working plus heating plus radiating, or work, heat, and radiation. Okay, so if we look at the next page here, we can see here it shows that the energy transferring into and out of a system affects the nature of the energy storage in the system. The first law of thermodynamics is also called the law of conservation of energy, which states that the algebraic sum of the energy changes and transfers between a system and its surroundings must add up to zero, which then accounts for all the changes relative to the system. All right? So the changes add up to zero. All right? The changes add up to zero. So what's lost by the system is gained by the surroundings, and vice versa. All right? So here we have heating, Q. We have working, W. And we have radiating, R. And this circle here is our system. All right? And Q, remember, involves three different types of energy accounts. Okay? Heating involves thermal energy, phase energy, and chemical energy. All right, so don't forget that. Okay? So energy in the kinetic molecular theory. So this is one of the really important theories in chemistry. We've been going over it. It accounts for the behavior of substances during all sorts of physical changes. All right? There are three key points. Matter is made of tiny particles that are in constant motion. We've said that. Just depends on how much space they got to move. Remember? These particles exert long-range attractions and short-range repulsions on one another. Attractions bring about a reduction in the energy state. The stronger those attractions, the lower the phase energy, remember? Because they can't move as well. Repulsions bring about an increase in the energy. And a hotter sample is one whose particles are moving faster than the particles are in a colder one. Okay? All right. So energy and heating or cooling. Right? So energy then is a substance-like quantity that's always involved whenever a system undergoes change. Hotter to colder, faster to slower, higher to lower, whatever. An exchange of energy has occurred. One of those things has happened. So a key to understanding energy is to recognize that energy is always and everywhere only energy. Energy is stored in different accounts, can be transferred between a system and its surroundings in different ways, but does not come in different forms. And there's a change in the way a system stores energy, or if energy is transferred between a system and the surroundings, then something about the system changes, not the energy. All right, the energy remains the same. So one problem we can have in understanding energy is that our everyday use of the words can sometimes cause confusion. For example, use of the word heat can leave the impression that it's somehow different from energy. It would be better if we view heat as one of the ways that energy is transferred, such as in the word heating. All right. While it's helpful to say that we heat an object as a shortcut for saying, well, we're transferring energy to it, it's not useful to say that an object stores heat. It stores energy. All right. It's fine to describe an object that stores a lot of thermal energy as hot, but saying that it stores a lot of heat confuses energy with the way that it's moved. All right. It's confusing heat with heating. So heating a system increases its thermal energy through the collisions of more energetic particles with particles of lower energy, and as a result, the particles in the system move more rapidly than they did before. So using that ing ending helps us view heating as a process of energy transfer, or rather than as something completely different from energy. The quantity of energy transferred in this way is often referred to as heat, which we assign the variable Q, but it's important to remember that it's simply energy. Conversely, then, a system cools when its particles transfer thermal energy to particles in the surroundings. In other words, energy is going out of the system into the surroundings. And that would then lower the amount of thermal energy that a substance possesses. All right. So let's look real quick at heating within a single phase of matter. So basically, we're looking at one little section of a heating curve, all right? So let's say we're talking about liquid water, all right? Liquid water remains liquid water above 0 degrees Celsius and below 100, all right? If you heat it or cool it within that temperature range, it's staying a liquid, all right? So we'll say we're going to heat it. So here's our initial temperature. This is, again, temperature in degrees Celsius. This is time. So this would be our initial temperature. And we're going to, let's say, heat water up from 25 degrees Celsius to 75. All right, it's going to stay water. So we heat it up. Let's say this is our final temperature. Say it's 75 for the sake of argument. So we had an increase in thermal energy, right? We're staying in a single phase of matter, and the change in temperature between final and initial is called delta T, right? Or delta in front of a variable means the change in. Delta T is the change in temp. It's going from a lower temperature to a higher temperature. So T final is greater than T initial, which means delta T is positive. You can see that on the graph. It's going that way, all right? If we're cooling within a single phase of matter, all right? Well, now let's say, again, so this is temperature in degrees Celsius, this is time. So now let's say we're going to start at 75 degrees. Say we're still with water. So here's our initial temperature now, okay? And now we're going to cool it down. We're going to keep it in the same phase of matter. So again, a change in temp signifies a change in thermal energy. Now our final temperature is down here, all right? So again, this is the change in temperature. But now our initial temperature is smaller than our final temperature is smaller than our initial temperature. So now TF minus TI, or the delta T, or the change in temp, has decreased. It's gone this direction, all right, which is in the negative direction. So now delta T is negative, all right? Delta T is negative, okay? So temperature is a useful tool because it allows us to assign a numerical value that helps us to describe the thermal energy of a system or its surroundings. Again, it's important to recognize that temperature and energy are not the same. Temperature, by definition, is actually a measure of the average kinetic energy of a substance's particles. Kinetic energy, again, involves their motion. Changes in temperature, or delta T, help us to determine the amount of thermal energy that is gained or lost, all right, by a system, as we shall discuss more later. All right. So we're now ready to discuss the role of energy during a phase change. So we'll first examine what happens when a solid undergoes a phase change due to melting and then again due to boiling. So as energy is transferred into the system, the thermal energy increases at some temperature, though the particles are vibrating to and fro so rapidly that they can no longer maintain their orderly arrangement. They break free of those attractions because they're moving too fast, and they begin to move around more freely, which is when they become a liquid. All right. We'll use another account to describe the way the system stores energy when the particles, undergo the phase change between solid and liquid, which we call phase energy. All right, called phase energy. So these phase changes occur at either the melting point or the boiling point of a substance. All right. So this is a little diagram of phase change only. All right, a phase change only. So let's say, and there are two. All right. So let's say we're talking about water. So this is T in Celsius, this is time. So let's say we're talking about going from ice to liquid water. So during that phase change, all right, there is no change in temp. There's just a change in the particle arrangement, all right? They're going from closer together to farther apart, from solid to liquid, all right? So this would be occurring at its melting point temperature. Melting point, all right? Once it goes to the liquid phase, and let's say we're then just going to boil it, this would then be the boiling point temperature. Boiling point. Again, it's a change in phase energy. We're going from liquid to gas, all right? No change in temp, all right? At a phase change, you get a change in phase energy. Different account, all right? Now, here I'm showing a relatively small amount of time, all right? What if I was showing one for a larger sample of the same substance? Well, there's more particles. It's going to take longer, right, for them to melt or boil, as the case may be. So we draw a little longer. Saying it occurs at the same temperature, but this would represent a small sample or smaller sample, and this would represent a larger sample over here. Again, the key is no change in temp with a change in phase or change in state. That is simply a change in phase energy, which is the particle attractions, all right? So that's a lot to take in for one day, so we're going to stop right there for today. You have an assignment that's due tomorrow, all right? Don't forget about that. Also, you got that big review packet, the first one of 3 for the fall semester exam. Be working on that. That is due this coming Tuesday, 7:30 a.m. or not 7:30. Sorry, that's mastering. Due at the beginning of your class period. Again, no answer key posted for that. So you need to be making sure you're working very carefully. And I would check with my friends and classmates and make sure you've done everything right, so that you don't. Hopefully, we'll catch some mistakes, either yours or theirs, in checking with them. So that would be my advice for doing that. So until next time, this is Mr. Keister signing off. Until then, stay safe, keep working hard, stay focused, and I will catch you next time. So long, everybody.